Hey, this is Professor Gilmet, and I wanted to do a video on sampling distributions, and so I've sort of titled it, How Can I Feel Safe After All of This Has Happened? And so, again, I'm continuing with my Arrow theme. So Season 1 of Arrow ended with a huge earthquake called the Undertaking that Oliver Queen's father was involved in. And there was a lot of destruction and loss associated with it, and the city needed to find a way to rebuild afterward, but with the rebuilding came a lot of looting and crime, right? So original Team Arrow, Oliver, John, and Felicity really have their hands full. And so the Starling City Sentinel took a poll and is reporting that 60% of residents do not feel safe since the Undertaking and increase in crime. So what is the probability that less than half of a random sample of 100 residents do not feel safe? Okay, so we saw in the video series that samples actually vary, and that the central limit theorem tells us that sampling distributions become normal when assumptions are met. So to answer the question, we need to do the following. We need to check our assumptions to make sure that the normal model is reasonable, model our sampling distribution with the information that they gave us, actually calculate the probability based on that unique model, and then state our conclusion in the context of this particular problem. So it's basically 4 steps, right? Now, we're going to start with the assumptions. And so, of course, the first assumption is that it's random. And so in the situation, it actually tells us that it is a random sample. So far, so good. The second assumption is independence. So will one sample of residents influence another sample? Probably not, okay? This condition would be violated if for some reason one sample did interact with or influence another or cause some sort of change, right? The third assumption is less than 10% of the population. And so, as I've done in class, I actually use a more intuitive formula to determine this. And that formula is 10 times n should be less than the population. And so I find this lends itself to more natural thinking. So even if you don't know the exact population size, you can just need to feel comfortable you are below it. And so for our situation, we have 10 times 100 is 1,000. Is 1,000 less than the number of residents in Starling City? And so as Starling City is a metropolis of about 2.5 million people according to the DC Wiki page, this seems completely reasonable. All right. The fourth assumption is sample size. I'm going to scroll up for this one. Okay. So this is really important because if this is not met, our distribution will not be normal enough, right? There could be skewness or it could be bimodal or something. And our calculation will not yield good results. So because we are dealing with proportions, we need to use the success-failure condition. If we were using means, it would be slightly different, but here we're using proportions, so it's the success-failure condition. And this means we need 10 successes and 10 failures in our sample. And so the formulas are n times p has to be greater than 10, and n times 1 minus p has to be greater than 10. Please note for some of you, the 1 minus p is going to be q. Oh, I'm still using 1 minus p instead of q as I find it less confusing for students. All right, just my personal experience. For our situation, we have 100 is our sample size. 60% of residents feel fearful. And so that's 60 residents who feel afraid after the Undertaking, which is greater than 10. And then, of course, below it, we have our other one. And, of course, 40 is greater than 10. So 10 successes, 10 people who are afraid. 40 failures, people who are not afraid. Note the successes plus the failures always equals the sample size. All right, this will help you do the calculations and check your work. So now we see that all the assumptions are met. So we are confident that we will have a normal distribution of samples. And this means we can actually now construct our model using the normal distribution. So how do I construct the model? Well, first you identify your center and calculate your standard deviation. Here we note that the report from Starling City Sentinel shows that 60% of residents do not feel safe. So this means our center is 60. that the proportion of residents that do not feel safe is 0.6. Okay, so that's our P. Now we need to calculate the standard deviation of sample proportions. And remember that formula is given here. Again, the 1 minus P is used instead of Q. All right, just keep that in mind as you watch these videos. Now, note, we are not simply multiplying by P hat. This is actually function notation, right? So this P hat in here that you see is a function of the standard deviation. All the little samples are acting as independent variables that influence the standard deviation function. So plugging in, we obtain 0.049, all right, to 3 decimal places. So now we're able to draw a picture and label it. And so we do this just as we always do. We put P in the center and then add and subtract the value of the standard deviation. Okay? So in the end, it should look like this. And so it should be this picture right here, where you can see the 0.6 is in the middle. And then if I add the 0.049, I'm going to get 1 standard deviation above. Adding the 0.049 again, I'm going to get the 698. Subtracting, we're going to go in this direction. And so these are 3 standard deviations below and 3 standard deviations above. So third, you want to mark your sample statistic P hat. Now, this situation is asking about samples less than 50%. So, P hat is 0.5, the sample proportion of residents that do not feel safe. So you mark this on your model and shade to the left because we want less than 50% to be afraid. This would be like a critical tipping point, right? When less than half the residents feel afraid, then maybe things go more normal. So we're going to mark this on our model, and you can see 0.5 is going to be just below 2 standard deviations, and the shading is to the left because of the less than. Okay, so we can see this is not a very likely outcome, but what is the actual probability, right? So the fourth thing that we do is calculate the z-score and then the probability. How do we calculate the z-score? Well, we're going to use the following formula. The z-score is basically the value minus the center divided by the standard deviation. All right. So for our situation, we're going to have 0.5 minus 0.6 divided by 0.049, and that's going to give us negative 2.041. And so that's negative 2.04 standard deviations, right? And it's going to be below the center. Now note, you do not have to calculate the z-score if you know how to change the mean and the standard deviation in your calculator or StatCrunch, but it is a good habit, and some professors are going to require you to show this step, right? So that's why it's here. Note also that I like to make my sample the subscript of the z-score so I can keep everything organized, especially if it's a multi-part problem and I'm going to be calculating several z-scores. So this is really important when you have several calculations, all right? The interpretation of the z-score is a sample proportion of 50% is 2.041 standard deviations below the population proportion of 60%. So sort of normalized the results to 2.041 standard deviations below. And so now we're going to plug this information into your calculator or into StatCrunch, and I'm going to demo how you get this picture here right now. So I'm going to go to StatCrunch and scroll up just a little bit so you can see. I'm going to click on Stat, Calculator, Normal, right? And so I'm going to find my probability of values less than negative 2.041 standard deviations below. And when I compute it, I can see, look, it's in the exact same spot. The shading is in the exact same spot. And it tells me that it's 0.0204 probability. right? So the probability is this value right here. Okay? So now we're ready to and that's this result, right? That's what I got right here. And so we see the p-value is 0.0206, which equates to about 2.1%. Okay? Please notice that even though the scale on the horizontal axis is different, the shading and placement is exactly the same. Okay? So even if you had changed it, right, and not calculated the z-score, you would still get the same thing. Okay? So now we're ready to state the conclusion in the context of the problem. And so given a sample size of 100 residents, because the sample size is really important, right? If it's not 100 residents, the standard deviation is going to be different. The probability of obtaining a sample of 50% or less of residents, that's my population, that do not feel safe, that's my trait, is 2.1%. Each piece is really important. Notice the pattern, and you can follow it as a model sentence. Given a sample size n, the number, the probability of obtaining a sample of whatever the sample proportion and the direction is, of whatever your population is, that trait, whatever your trait is that p-value probably as a percentage, right? So everything that's underlined is the thing that you're going to change for the context of the problem. And so now you can do sampling distribution problems, and that makes us happy. Stay tuned for more stats videos, and this summer I'm going to be doing some more liberal arts math videos. All right?